Hello students, I want to talk to you about our acid-based decision-based learning lesson. And the first thing is, I want to just mention briefly, what is decision-based learning? Decision-based learning is just a strategy that I'm using to help you be able to translate what you see when you look at a problem into an action that you're going to take. So I'm going to ask you to look for clues or features of the problem. For example, in this case, is it a strong acid? Is it a weak acid? Is it a strong base? Is it a weak base? Is it a buffer? Is it a mixture of some of those things? So you're going to look at that information, and then you're going to have a series of decisions that you're going to make. So based on that information, what should I do next? And we're going to use the information that we have, the concepts that we understand about strong and weak things and buffers, to help us answer these questions so that we can figure out what to do. So it's not just memorizing, this is the procedure that always works, because this is really complex. There's all different ways that you can combine these things together, and what you do with them is going to change depending on how much of them you have, how they relate to each other, whether they react or they don't react. And so we have to use all of those concepts, like strong acids and strong bases are going to dissociate completely and react completely or stoichiometrically. Weak acids and bases are going to be governed by an equilibrium. If I have a weak acid, it's going to react with water to make the conjugate base an H3O+. If I have a weak base, it reacts with water to make the conjugate acid an OH-. All of those ideas, those big picture ideas, are coming into play here as we are making these decisions. So that's the first thing, just an introduction to the idea of what we're talking about. Now, the next thing that I want to talk about is I'm going to go through this example, the table that we used in class, where we're mixing together different things and then deciding what to do. So the first thing is, what if we just have a strong acid in water? The goal of all of this is to calculate the pH. If I have a strong acid in water, then the procedure that I'm going to do is pH equals negative log of the H+ concentration. That's all I'm going to do. Pretty straightforward. If I have a strong base in water, then my procedure is going to be pH equals 14 minus the negative log of the OH- concentration. This, of course, is the POH. Also pretty straightforward. I'm doing this. Why do I make these decisions? Because we know that the strong acids and bases dissociate completely. So I don't have to do anything tricky to figure out how much H+ or how much OH- there is. Just how many moles do I have there and what's the volume, and then I can figure it out. Okay, now what if I have a weak acid in water? Well, then my procedure is going to be that I'm going to use a Rice table with the Ka for that weak acid. Why am I doing this? Well, weak acids dissociate only a little bit. So to figure out how much dissociates, I have to use a Rice table and get my X value by solving with my Ka that's given. Once I do that, I'm going to get a value of X, which is going to equal the concentration of H+ in my solution, and then I take the negative log of the H+. So in a sense, when I do my weak acid, I'm doing sort of the same thing here, right? As I did up here with my strong acid. The only difference is I'm going to be dealing with this equilibrium first. Okay, now what if instead I've got a weak base? Similar thing, I'm going to use a Rice table, but this time, because it's a base, I'm going to use the Kb value. When I get my X, that equals my concentration of OH-, and then I follow the same thing that I would have done for the strong base. pH equals 14 minus the negative log of the OH- concentration. Okay, last thing, if I have a buffer in water. I'm reviewing these all because everything else that we're going to come to in our decision tree is going to end up back in one of these places. You already saw that even with the weak acid. We do our rice table first, and then this is just the same thing as we did with a strong acid. With a weak base, we do our rice table first, and then this is the same thing we did with a strong base. So every time that we're making a decision, it's going to tell us, okay, go back to one of these boxes that we're starting with. Just what is that thing doing in water by itself? Okay, last one, we've got buffer. What's our procedure? We're here going to use the Henderson-Hasselbalch equation, pH equals pKa plus the log of the, I should do the other parentheses, concentration of A minus, which is our base, over the concentration of HA. Now, obviously, you could also have a neutral base. So sometimes you might have A over HA plus, right? Just a note there in case that comes up. Okay, so these are all of my fundamental, I run into an acid or base, it's just by itself in water, what am I going to do strategies. Now we're going to get to things that are more complicated. We're going to start mixing things together. Okay, the first one I want to talk about is what if we mix together a strong acid and a strong base. Now this is also known as a titration. If you're mixing together a strong acid and a strong base, depending on how you're doing it, in a titration, obviously you add the base, usually it's the base, really slowly so you can kind of map out the pH curve and everything as you're going along. But you could also just have a beaker of strong acid and a beaker of strong base and be mixing them together. Okay, so first things first, what do these guys do? It's an acid and a base, they're going to react with each other. That's the first thing. Okay, they're going to react. They do a neutralization reaction, and they're going to react stoichiometrically, meaning because they are strong, they just drive that reaction forward. There's not an equilibrium involved. They just react stoichiometrically, the same way that you learned when you just were learning regular old stoichiometry. How many moles of this do I have? How many moles of that do I have? Okay, that's the first thing that we need to take care of. Second thing, to do this, we're going to use our BCA table. And the BCA table is like a rice table, but we use moles, not concentration. And there's no X's. You just use the limiting reactant. So I'm going to show you 3 possible outcomes here, because if we're reacting these together stoichiometrically, it could be that we have stoichiometric amounts, an equal amount of both. Or it could be that we have one of them that is in excess. So there's 3 possibilities of the outcome. So I'm going to use an example of HCl and NaOH. I'm using these because they're classic strong acid, strong base. So if I have these together, now this is the trick, you guys. We know it's a strong acid and a strong base. We know they're going to react with each other. We have to be able to predict what the products are. In this case, they're acting like Arrhenius acids and bases. My H plus and my OH minus are going to get together and make water. And then the leftover stuff is going to give me a salt, in this case NaCl. Okay, so that's my reaction that's going to happen. Writing the reaction is a non-trivial exercise. You have to recognize what is the stuff that I have and what's it going to do. So you have to be able to predict those products, figure out what's reacting, and write out the reaction for that. Okay, now I'm going to go through 3 examples here. The first example that I'm going to do, this is my BCA table, so before, change, and after. I'm going to have half a mole of HCl and 1 mole of NaOH. And if we want to be like more precise about this, let's say we have 1 liter of 1 molar NaOH and half a liter of 1 molar HCl. Okay, just keep it kind of simple here, but that's what we've got. We're mixing together. Now, these are the things that I'm starting with. They're going to react stoichiometrically. In this case, HCl is my limiting reactant. It's going to be completely used up, and then we're going to get some of these other things Like we'll get some NaCl that's formed. My HCl at the end will be 0, my NaOH will be 0.5, and my NaCl is 0.5. Now, when I get to the end of my BCA table, and this is the other thing that's hard, when I get to the end, I have to ask myself, what do I have? Okay, and in this case, I have 0.5 moles of NaCl. This one is a neutral salt. It doesn't have any acidic or basic character because it's just made from Na ions. They're all spectator ions, right? They're not doing anything interesting. So I'm going to just ignore that one. Okay, the other thing that I've got is half a mole of NaOH. This one here is going to affect my pH. So what I'm going to do now is I need to calculate the concentration of my hydroxide ions. I've got 0.5 moles. And now, because I mixed these guys together, I actually have 1.5 liters, which means, oh gosh, that's 0.33 a molar. And I'm going to take the negative log of that. So that gives me the negative log of 0.33 gives me my pOH, which is 0.48. So when I want to find my pH, it's just 14 minus that, which is 13.52. And that makes sense because I've got a bunch of NaOH left over, so it makes sense that 13.52 would be my pH. Okay, this was the first example of what could happen if I'm mixing together the strong acid and the strong base. First thing I had to do is figure out what reaction is happening. Second thing, use my BCA table to figure out how much of what stuff is going to be left over at the end. And then third thing, use my brain to see which of those things do I have to pay attention to. Okay, I'm going to do another example now, and I'm going to end up with a 1-to-1 ratio. So we're going to do a BCA table again. We've got HCl and NaOH. We're making water and NaCl. This time I'm going to have 1 mole of each. I'm going to end up at the end with none of this acid, none of this base, and I'm going to have 1 mole of NaCl that's left over. In this case, it would be 1 mole of NaCl, and it would be in 2 liters. But we're going to ask ourselves, what is this thing? It's a neutral salt. In other words, it's not going to affect the pH at all. So my pH equals 7. I don't have to do anything extra or special because my water is not going to be affected by the presence of NaCl. Okay, third situation now, I'm going to have, instead of having too little HCl, like I did in this first example, I'm going to have too much HCl. So I'm going to do the same thing, HCl plus NaOH. We're making water and NaCl. And this time I'm going to have 2 moles. And again, let's again say that's 2 liters of 1 molar HCl, 1 liter of 1 molar NaOH. So here I'm going to subtract only 1 because my NaOH is now the limiting reactant. So I get 1 mole of HCl left over, my NaOH is used up, and I get 1 mole of NaCl. My NaCl, as we've discussed, we can ignore. It's a neutral salt, so it's not going to affect anything. My HCl, however, I've got now 1 mole in 3 liters total, which is 0.33 molar. I'll take the negative log of 0.33, and that gives me 0.48 as my pH. Okay, so a couple of things again that I want to point out. Number 1, we had to figure out our reaction. We have to write the reaction that's going to happen. We have to use our brains to do that. We have to reason about it. It's an acid and a base. They react together. What are the likely products? We have to predict what those products are. Second thing, we're going to take care of some stoichiometry using our BCA table. And then third thing, we're going to interpret the results here. What do I have at the end? In this case, I had a strong acid left over. In the prior case, I just had a salt and that didn't matter. And if I go back to the first example, I had excess base, and so that made a difference. Okay, that's what we did for our strong acid, strong base. Okay, now I'm going to move on and I'm going to be mixing a strong acid and a weak acid. Strong acid and weak acid. First thing, we're going to use our brains to think about this. We know strong acids dissociate completely. And that weak acids dissociate only partially. Okay, if that's the case, then we always deal with the strong thing first. Okay, now I'm going to purposefully do an example here that is a concentrated weak acid and a dilute strong acid. Okay, so I'm going to say we have 100 milliliters of solution and it contains 0.01 molar HCl and 1 molar CH3COOH, or acetic acid. The Ka for acetic acid is 1.8 times 10 to the minus 5. Okay, kind of a standard weak acid. So now what I'm going to do is I'm going to deal with the strong thing first. If I have the strong thing, I know that I have 0.01 molar H+. It dissociates completely, so that's my concentration of H+. And my pH would be 2. Negative log of 0.01. Okay, now we're going to take a look at what would happen next. So the first thing we did is we're dealing with that strong acid. It dissociates completely. But let's come back to our weak acid. Weak acids do have some activity in water. They can react with water. This is the K equation. Acetic acid plus water, the Ka equation. We get CH3COO minus, the conjugate base, and H3O plus. Okay, so now we're going to start with our 1 molar. We're going to do, this is our Ka equation, and we're going to do a Rice table. 0.01 molar of H+. That's the key thing. It was from our strong acid. It gets put right down here into our Rice table. And we've got 1 molar acetic acid. We still don't have any of our acetate, so we are going to have some forward motion on this reaction. And our Ka would be X times 0.01 plus X divided by 1 minus X. So we have to ask ourselves, can I neglect X here? My Ka is 1.8 times 10 to the minus 5. I'm starting with 1 times 10 to the minus 2. Because they're 3 orders of magnitude apart, I'm going to say yes, we can neglect X. So when we do this, we've got 1.8 times 10 to the minus 5. I'm going to multiply by 1. I'm going to divide by 0.01. And that's going to be my value of X, 0.0018. And now I can find what is my new H3O plus concentration. 0.01 plus 0.0018 gives me 0.0118 as my H plus concentration. Just adding those together like it says to do at the end of my Rice table. So now I've got my H plus concentration. I'm going to take the negative log of this. And when I do that, I get 1.93. So in this instance, when I had a weak acid that was 100 times more concentrated, we had a weak acid that was 100 times more concentrated than our strong acid, then it was necessary for us to do this second table. But if it weren't such a big difference, even if we had acetic acid that was 10 times more concentrated than the HCl, it would still be a very small amount. So if my ratio of weak to strong is smaller than 10:1, then I can ignore the weak acid. It's only in instances where I have an extraordinary amount of that weak acid that I'm going to have to take that into account in my calculation. Most of the time, if I have a strong acid and a weak acid mixed together, I can ignore the weak acid. Only when I have more than 10 times as much weak acid as strong acid, then do I have to do this rice table as a follow-on. Okay. Good. We're doing great. Thanks for sticking with me here. Okay. Next, we're going to have a strong acid and a weak base. We're going to start with, what do we know about these things? We've got a strong acid. Strong acids react completely stoichiometrically. And we've got a weak base, which we know would have an equilibrium with water. And we know produces a weak acid when it's neutralized by the strong acid. Okay, so let's take a couple of examples here. We'll use HCl and NH3 for this. Okay, first thing I'm going to do, this is similar to what we did before when we had the strong acid and the strong base. I'm going to react these guys together and I'm going to figure out what do I make as products. In this case, because we've got a weak base, it's going to act like a Bronsted-Lowry base. It's going to accept the proton. Our acid is going to donate the proton. We get NH4 plus and Cl minus as our products. This is important because we're going from, in this reaction, we're actually producing the conjugate acid. So that's going to come back to give us more information as we're going along here, okay? We're going to have to take that into account. Again, we have the same three possibilities. Either we have excess HCl, or we have excess NH3, or we have stoichiometric quantities. So let's start with the same way we did before. We'll start with half a mole of HCl and 1 mole of NH3. Because this one is strong, we know it reacts stoichiometrically, so we're going to use a BCA table and not a rice table. And we'll assume that this is 0.5 liters of 1 molar HCl and 1 liter of 1 molar NH3. Okay. These are my moles. I don't have any of these guys over here. My chloride ion doesn't even really matter at all, but we'll just keep it there for kicks. We're going to react stoichiometrically, so we're going to use up all of the HCl. We'll end up with no HCl left, but we'll have half a mole of NH3 left. Notice we also have half a mole of NH4 plus and half a mole of Cl minus. So I'm going to ask myself, now that I've got to the end of my BCA table, I've got to interpret what do I have that matters. I'm going to first get rid of my Cl minus because Cl minus doesn't have any acidic or basic activity in water. However, I notice that I've got a combination now of my weak base and its conjugate acid. This is, in fact, a buffer. And so I'm going to use, because it's a buffer, I'm going to use my Henderson-Hasselbalch equation, pH equals pKa plus the log of AHA. That'll be NH3 over NH4 plus. Concentrations, of course. Now, it turns out these are actually equal to each other, and this whole term is 0. So I know that my pH equals my pKa. Our NH3 has a Kb of 1.8 times 10 to the minus 5. And that means NH4 plus has a Ka, it's just Kw over Kb, of 5.5 times 10 to the minus 10th. So all I have to do is take the negative log of that, which gives me 9.26 for my pH. So when I have my HCl all used up, I've reacted some of the base, the weak base, but not all of it, because the product of that reaction is the conjugate acid, NH4+. That means I have to consider this a buffer. This is why it's so important when you see this strong acid in the weak base that you know how to predict what are the products of that reaction going to be. Because if the products are going to have something that has any kind of acidic or basic activity, we have to take that into account. So this is my first example. I ran out of acid. I had extra of my weak base. I ended up making a buffer. Now I'm going to do another example here, and I'm going to have equal quantities. So I'm going to have HCl and NH3. When they react, they make NH4+ and Cl-. And our Ka for NH4+ was 5.5 times 10 to the minus 10. Okay, now I'm going to have equal amounts. 1 liter of each of them. I'm going to react it completely. My acid and base are completely used up. Now I have some Cl-, which I'm again going to ignore for the same reason I did last time. Doesn't have any acidic or basic activity, but notice what else I've got. Now I have 1 mole of NH4+. Because I was using 1 liter of each of these, my 1 mole of NH4+ is distributed in 2 liters of solution. Because remember, we're using our 1 molar HCl, our 1 molar NH3, so this is 2 liters that I've combined together here. So that gives me 0.5 molar NH4+. And now I'm going to remind myself, what is this thing? That is a weak acid. What do I do with a weak acid? I'm going to need to do a Rice table, and I'm going to use the Ka equation. So after I do my BCA, I realize now I need to take care of this NH4+. It's a weak acid. What do weak acids do? They react with water. There's an equilibrium. They make the conjugate base and H3O+. This is our Ka. So I've got 0.5 molar NH4+. I'm going to lose a little bit there, gain a little bit here. I'm going to get x squared over 0.5 minus x. What's happening here, pencil? Okay. X squared over 0.5 minus x. Can I neglect x? I think I can. We've got 10 orders of magnitude difference. So I'm going to take 5.5 times 10 to the minus 10. I'm going to times by 0.5. And then I'm going to take the square root of that to solve for x. And I get 1.66 times, this is so weird, 10 to the minus 1, 2, 3, 4, 5 as my value of x. So going back over here, it's true that I can for sure neglect it there, but I'm going to have a concentration of H3O+. Okay, pencil. That's going to be 1.66 times 10 to the minus 5. So to find my pH, I'm going to take the negative log of 1.66 times 10 to the minus 5. And that gives me 4.78 as my pH. That makes sense. I expect this to be acidic because I have a weak acid in my solution, NH4+. Okay, so that's our second situation now, where we started with equal quantities of our strong acid and our weak base. We're going to do one more situation. We're going to start with excess of our HCl compared to our NH3. The same reaction is going to happen here. We make NH4+ and Cl-, but now I'm going to start with 2 moles of HCl and 1 mole of NH3. I can only react away 1 mole, and now I'm going to end up with a mixture of a strong acid and a weak acid. Because these are equal concentrations, I know I can ignore the weak acid because the strong acid is going to dominate. My concentration of HCl I have 1 mole of HCl here, but I actually had it in 3 liters because I had 2 liters of HCl and 1 liter of NH3. So that gives me a concentration of 0.33. If I take the negative log of 0.33, that gives me my pH, which is 0.48. So I end up with an excess of HCl. I'm only taking into account my concentration of my strong acid, my moles of strong acid, because the weak acid isn't going to matter because it's the same concentration. I only have to worry about the weak acid if it's like more than 10 times as much as the strong acid. Okay, we did such a great job. We made it through strong acid and weak base. Now, we're going to move on. We're moving on to strong acid and a buffer. What happens when I mix those together? This is tricky, okay, because the buffer already has 2 things in it, right? Weak acid and its conjugate base. So now we actually have 3 things in our container. And so it makes it a little bit more challenging to decide what's going to react. Okay, so let's say we've got HCl, and for our buffer, we're going to have acetic acid. Oh my gosh, come on. Okay. CH3COOH and acetate CH3COO-. To keep our lives easy here, we're going to say we've got 1 molar HCl that we're going to work with, and we've got our buffer is going to have 1 molar. Our buffer is going to have 1 molar acetic acid, and also in the same liter, 1 molar CH3COO-, the acetate. This is all, in a single liter. That's the buffer mixed together. Okay, now the same principles apply here. I've got a strong acid, and then I have the buffer. The buffer is made up of weak things. Whenever I have something strong, I have to take care of that first. I have to take care of it first because it's going to react stoichiometrically, okay? So we're going to imagine for ourselves a couple of situations. First thing, if I've got this strong acid, what's it going to react with? Does it react with the acidic part of the buffer? It does not. It's going to react with the basic part of the buffer. So I'm going to have HCl and I'm going to have acetate. I'm using my single arrow because this reacts stoichiometrically. I'm going to make acetic acid and chloride ions. The chloride ions don't really matter here, but that's okay. Okay, so this is the reaction that's going to happen. How did I decide? I know that acids react with bases. I only had 1 base there, and it was acetate. So that's what I did. Notice I did not include my acetic acid as a reactant. I didn't think about it at all, except when I did this reaction, I had to predict the products. And that's the product. If my acid donates its proton to the acetate, I get acetic acid. Okay, so now we've got the reaction of what's going to happen, and we're going to do 3 situations. We're going to start with a situation where we only are adding half a liter, half a mole of our HCl. And we've got 1 mole of acetate, 1 mole of acetic acid. It reacts stoichiometrically. I'm just ignoring the Cl here because it doesn't do anything interesting, so I'm not writing that down. But we end up here with, again, a mixture of a weak acid and its conjugate base. In other words, that's a buffer still. In order to do that, I'm going to use my Henderson-Hasselbalch equation, pH equals pKa plus the log, in this case, of acetate, CH3COO minus, divided by acetic acid, base over acid. Now, you might be wondering, gosh, these are moles. Do I need to change them into concentration to put them in this equation? You can if you want to, but because they're all in the same beaker, the volume is going to be the same and it ends up not mattering because it's a ratio of base to acid. So my pH here, my pKa is 4.74, and I'm going to add on the log of 0.5 over 1.5. which is negative 0.48. And I end up with 4.26 as my pH. I like to do a little gut check with myself. If 4.74 is the pKa, I look at my mixture and I've got more acid than I do base in my buffer, so I do expect the pH to be lower. So my pH would be 4.26 here. Okay, that's my first situation. Second situation that I'm going to add stoichiometric amounts of my HCl and my acetate. So still mixing that together with the buffer, but I'm going to add as much HCl as I have acetate. So I've got HCl plus acetate makes acetic acid and Cl minus. This time, I know that I've got 1 mole of each of these. I'm going to add 1 mole of my HCl. So it's all going to react stoichiometrically. I use up all of the acid in the base, the strong acid and base, a weak base, but now I'm left with 2 moles of this weak acid. So at the beginning, I had 1 liter of HCl and 1 liter of my buffer. That's 2 moles in 2 liters, which gives me 1 molar acetic acid. And I've got to consider now, what do I do? What does a weak acid do? Weak acids react with water to make the conjugate base and H3O+. That weak acid is going to have its own acidic activity in the water. This I've got to use a Rice table for because it's an equilibrium. I know that I have 1 molar of that. At this point, I don't have any of these left over because I used them all up. So I'm going to lose a little bit here, gain a little bit here, and I end up with Ka, which is 1.8 times 10 to the minus 5 equals x squared over 1 minus x. I'm going to neglect x, and I get just the square root of this. X equals, 1.8 e minus 5. And then square root. I get 4.24 times 10 to the minus 3. That is safe to neglect from over here, but it is going to be my concentration of H3O+. And so I'll take the negative log of that. My pH will be 2.37. Okay, that's our second situation. Third situation, we add so much acid that we completely obliterate the buffer. We don't have any of those guys left. We're going to have excess acid. Okay, so in this case now, I've got HCl It's reacting with the base from the buffer, the acetate. It's going to make the conjugate acid, acetic acid, and Cl-. This time I'm going to have 2 moles of the HCl and 1 mole of my buffer, 1 mole of each of these. And I'm going to react it stoichiometrically. There's only 1 mole to react. So I'm going to end up with now a mixture of a strong acid and a weak acid. And what do? There isn't as much as 10 times as much of my weak acid, so I'm going to ignore it. I'm going to ignore the weak acid, and I'm going to calculate my pH from just the HCl. I've got 1 mole of HCl, and I combined 3 liters of solution. 2 liters of the HCl, 1 liter of the buffer. That gives me 0.33 molar. Negative log of 0.33 is 0.48. That's my pH. Okay, good. Now, I want to talk about this one last time, this example that I just did. Notice I started with, oopsie, come on. Okay. Notice in each situation here, I did this 3 times. And in each situation, what I was doing was doing my BCA table and then reevaluating. What do I have? In this case, I said first I was starting with my strong acid and a buffer. I did my BCA table. After my BCA table, I realized I had a mixture of a strong acid and a weak acid. And then I ignored the weak acid. And then I ended up just deciding this was a strong acid. So you can see how in the end, even though we went through several iterations here, in the end, and I'm going to scroll back up here, it'll probably look terrible. In the end, we always come back to one of these 5 procedures. In this case, we ended up just having a strong acid when we were that was left over. There are, of course, strong base and weak acid, strong base and weak base, strong base and buffer, but those are all parallel to the ones that we did with strong acid and weak acid, strong acid, and weak base and strong acid and buffer. So the strategy for solutions is very similar. The last one that I would want to do is what if you have a mixture of a weak acid and a weak base? This one's a little tricky because we know that they don't dissociate completely. They're both going to have these equilibria that are happening. And so what can we do in this situation? And in this situation, what we would want to do is look at the Ka for our weak acid and the Kb for our weak base. And whichever one is larger, we're going to ignore. So in this case, let's say our Ka for the acid is greater than our Kb for the base. And let's say it's by a couple orders of magnitude, okay? Ka is bigger than the Kb. What do? We just ignore this and we calculate it entirely with the Ka. This is in fact what you'd see also if sometimes you have something like a salt like NH4 HCO3 or something like this, where you've got an acidic NH4 plus and a basic HCO3 minus. You look up the Ka value and the Kb value. The Ka for NH4 plus, we already know. It is 5.5 times 10 to the minus 10. The Kb for HCO3 minus is going to be 2.1 times 10 to the minus 4. So which one am I going to ignore here? I'm going to ignore the Ka, and I'm going to calculate it just as if this is the one that matters. So this is similar to where you might have a salt that has parent weak acid and weak base, and therefore contains a weak acid and a weak base. You would compare them that way. Okay, I want to review a couple of key points. First thing, identify the stuff. Do you have strong acid, strong base, weak acid, weak base, buffer, or some combination? That's the first thing. Once you know that you can treat these. They react completely. They react stoichiometrically. These guys are going to have some kind of equilibrium, as is actually the buffer. There's an equilibrium. Okay? That's the first thing. Figure out what it is. Second thing, write the reaction that will occur. Write the reaction that will occur. This is non-trivial, okay? So you've got to be able to identify it's going to be some acid reacting with some base. And then you've got to predict the products. If you're using Arrhenius, like if you have a strong acid and a strong base, you might get water and a salt. Or if you've got a weak acid or something like that, you might need to use the Bronsted-Lowry with like H plus donors for acid, H plus acceptor for your base. Okay, that's the reaction that's going to occur. You're going to predict the products that way. Now, I want to point out, what if all you have is a weak acid? It still has a reaction. The reaction is the Ka. If you have a weak base, it still has a reaction. The reaction is the Kb reaction. So that's the first thing, write out the reaction. If you're doing something that's stoichiometric, like these guys, you're going to use our BCA table. If you've got an equilibrium, you're going to use a Rice table. That's the second thing. Third thing, when you get to the end of the table, either of the BCA or the Rice table, you have to then interpret. Ask yourself again, what stuff is here? In other words, you're looping back from number 3 up to number 1. And you do this until you end up, at the end, you're always going to end up with one of these 5 situations: strong acid, strong base, weak acid, weak base, or buffer. Okay, that's the end. Thanks for hanging in there and listening, and I hope this is helpful.